Okay, great. Thanks a lot for the invitation and greetings from central Illinois. It is around 4:13 here. And I'm glad to see that the conference was moved into the virtual mode. I think this is a beginning of things to come over the next year, and this will provide new innovative ways to try to have these conferences and bring speakers from around the world. Um, as Marek said, my name is Eliu Huerta. I am the director of the Center for Artificial Intelligence Innovation at the University of Illinois at Urbana-Champaign. And in this talk, I want to share with you three areas where we have been exploring the convergence of AI and high-performance computing. And it is, I think, in order to say that it is not just the physics community that is exploring the convergence of AI and HPC. It is a common theme in many different domains, from genomics to biology. But for the things that I understand well and that I have been contributing to, I want to cover three topics. The first one on the top left has to do with what I would call traditional applications of high performance computing. If you are dealing with big data problems, for example, if you're doing high energy physics and you produce big data sets in very low latency with particle accelerators, then you're interested in training neural networks with these data sets. But that entails the use of terabyte-sized datasets. So it is in order, as was described in the previous talk, to try to use distributed training algorithms to reduce the training stage to a minimum. Then we also have, in the top right, a different application of AI, and this has to do with optimizing software stacks that are very good to, for example, describe computational fluid dynamics, or, for example, the collision of two neutron stars. These simulations take a long time, and what happens most of the times is that the bottleneck is when you need to use very small grids to describe complex processes, for example, like turbulence. And so the question is whether we can use AI to accelerate those simulations. And I'm going to present some results that suggest that we can do this. And the final application is the convergence of HPC and AI to address problems that either HPC or AI are not able to address. And here I am talking about the need, for example, to combine distributed training and simulation on the fly, because the production of data sets could lead to exabytes of data, which is not good in terms of data storage. And on the other hand, you would have to anyways use thousands of GPUs to address this type of problem. So it is time to explore how we can try to bring these two together. Okay, so let's start with convergence of AI and HPC for big data problems. And here you're going to see a series of simulations. On the top right, you see a simulation of magnetohydrodynamics turbulence, in particular the Kelvin-Helmholtz instability. And what we have observed is that when you have high-resolution simulations, you tend to see a lot of these features that are hard to resolve with low-resolution simulations. On the left, you are seeing the collision of two neutron stars. This is a typical multi-scale, multi-physics simulation. It takes a long time, several months, to run one of these simulations to completion in a high-performance computing cluster. And then let's look at a different simulation. This is the collision of two black holes. It is a simulation that can be run in a couple of weeks with state-of-the-art software stacks. And the issue here is that when you try to study black hole mergers, you realize that they span a 9-dimensional parameter space. So if you want to use deep learning to do gravitational wave discovery, as we pioneered this area of research about 3 years ago, what you find is that you need about 1 billion waveforms to properly sample this parameter space. And then we are talking about exabyte datasets. So how do we go about sampling this parameter space and try to train neural nets in a feasible amount of time? So these are the three topics I want to cover. So reducing the time to insight. As I said before, there are a lot of large-scale projects in the US and Europe and Asia that deal with really big data sets. For example, high-energy physics, particle physicists are at the point where they need to figure out on the fly, when the data is being produced, whether some chunks of data are worth processing or not. Not even at the level of, okay, I have my data sets, I'm going to process them now. It's even before that happens that they need to make these decisions, and they are using AI for this type of work. When it comes to multi-messenger astrophysics, here we're talking about combining gravitational wave detections with electromagnetic and neutrino detections in real time. So this is a multifaceted problem because gravitational waves are lightweight. It's not a lot of data, a few megabytes per second. But then you have images that are produced very rapidly, and there you have millions of different transients in every image, and then you need to process this and try to identify whether there is something new popping up from one image to the next to see whether there is an electromagnetic counterpart. So processing all of this information in real time requires the ability to not only fuse data, but also extract meaningful information in data sets that are very noisy. And then you have genomics where there is a lot of data, it's not being labeled properly, and this complicates the application of AI. So let's go to the scenario that has been emerging over the last few years, which has to do with using big data sets to train neural networks and try to obtain state-of-the-art accuracy that is comparable to existing algorithms, but that are much faster and that enable you to do new physics. This also requires, since the community is not very knowledgeable of AI applications, to try to turn these black boxes into gray models. In different words, that we are able to interpret these neural networks and to understand how they are abstracting information and then producing interpretations. So to give you an example, something that is considered an archetypical application of deep neural networks is image classification. So on the top left, you have an image of a very successful citizen science campaign, which is the Galaxy Zoo project. They partner with the Sloan Human Label about 1 million images of galaxies. We're one of the largest data sets that has been curated by humans. And that was a very successful approach, but that was a survey that was completed years ago. Now look at the bottom right. This is now the dark energy survey. Now here we have about 300 million galaxies. So citizen science, though very effective, might not be scalable to go and try to curate these images. And I'm pretty sure that students would not be happy trying to do this. So it is necessary to try to explore new avenues to do data curation and then classification. So something that we have done, and you can see here, is to use neural networks and then a combination of different techniques to do this at a scale. And here the name of the game is we use the state-of-the-art neural net. This is back in 2018 for the ImageNet classification challenge, which consists of a dataset ImageNet that has millions of images labeled by humans that span thousands of different categories. So we use these pre-trained neural nets and then go and extract about 36,000 galaxy images classified by Galaxy Zoo and apply transfer learning, which is very common in the AI community. Basically, you start on freezing the layers of the neural net from the one that is at the very bottom, which contains the most abstraction, and then you unfreeze the layers gradually. And I will show you an animation of how this works. But what I want to show you is that when we use the Cooley supercomputer in Argo National Lab, we were able to reduce the training stage from about 5 hours to just 8 minutes using 64 GPUs. Now, admittedly, these are K80s. These are not, the new generation of GPUs. But if we use the HAL cluster, that stands for Hardware Accelerated Learning Cluster, at the National Center for Supercomputing Applications, with just 64 voltas, we can reduce this to just 2.7 minutes. So this is now giving us the ability to go and explore new things. For example, physics-inspired AI architectures or optimization schemes. Now, this all looks really good. We were able to not only obtain state-of-the-art classification accuracy for images that were collected by the Sloan, but also by the Dark Energy Survey. But most importantly, we were able to turn the neural network from being just a classifier into a feature extractor, which means that we can now feed unlabeled images from the Dark Energy Survey that have not been observed by any other survey, and then obtain the right classification for the galaxies. In different words, we automated data curation, bypassing the need of grad or undergrad students to do this work. Now, in this visualization, what I want to show you is how we are using the neural network to get new insights into how neural nets process information. So as I said, we have a set of galaxies, spiral and elliptical, collected by the Sloan Digital Sky Survey. We want to see how the neural net is abstracting information as we do transfer learning. So we have this mosaic of different galaxies. You can see some of them are very noisy, some others are really bright. And we have two types, spiral to the right, elliptical to the left. In different words, a lot of structure in spiral, not a lot in elliptical. So let's see how a neural net tries to figure out which image represents which galaxy. And so we're going to start with transfer learning. You are going to see on the left that since the elliptical galaxy does not have a lot of structure, there will be spike in the values that the neurons get on each of these layers as the training proceeds. You can see that the spiral gets the first spike in the output values very late in the game because it is learning. It has a lot to learn from the morphology of the galaxy. Now, when you overlay these two sheets of output values, you are going to see that the two data sets in blue and yellow form an orthogonal data set. And when you look at the last layer, you're going to see here that when you have zeros for elliptical, then you have high values for spiral, and vice versa. In different words, they are representing orthogonal data sets. But now let's do this on the fly, seeing how the neural net is gradually labeling the images. So here we have the galaxies, and you see that in red, you have a lot of misclassifications because the training is starting. Now, as the training goes on, the neural net is learning more and more, and now gradually it assigns the correct label to each galaxy. It's not only that, but also the neural net realizes that these two images form two independent, orthogonal, non-overlapping datasets. So this is how the net learned information, and this is the output, which is pretty cool. This was presented at SCFE20 last November in the Visualization Challenge. Now, let's move on to different scaling applications of neural nets. One of the key issues that we have in gravitational wave astrophysics is estimating the parameters of gravitational wave sources. And we presented for the first time the application of Bayesian neural nets for this type of work. Now, the applications that we introduced back in 2017 describes a parameter space that cover only two dimensions, the masses of the black holes. Now we are training models that take into account the masses and the spins of the black holes. And back in 2017, we only required 40,000 model waveforms to train the nets. But when you now consider a four-dimensional parameter space, if the spin vector is only in the z direction, then we now need 30 million waveforms to train these models. And if you now consider that Bayesian neural nets require the tuning of twice as many parameters as for deterministic models, then you see why it is needed to use supercomputers. And here you can see the number of nodes that we use in the Theta supercomputer at Argonne National Lab to train one of these Bayesian neural nets at scale for the first time. And this is a paper that is in review right now, where we show that these applications can be used to estimate the parameters of black hole mergers within a few seconds, as opposed to days or weeks using traditional Bayesian data analysis. Now, let me talk about the second topic, which is accelerating software stacks to model, for example, computational fluid dynamics. I'm going to focus on a problem that is a big issue for neutron star mergers, which is turbulence. And so if you look at these different simulations from right to left, you're going to see that they vary in resolution from top to low resolution to the left. And as you can see in the high resolution simulation, you see a lot of features that are produced by turbulence that are not evident in the low resolution simulations. Now, truth be told, when you get an allocation in a high performance computing platform, you will only be able to run a few high quality simulations. So the question is, how can I maximize these resources and the science I do with them? So what we have done is to use deep neural networks to train models with these simulations, and then use the model to learn features at the grid scale. And then we identified a few features that were to learn and to describe. And one of them has to do with the magnetic fields. And so here we show results from how the neural net is learning the features that magnetic fields drive in these simulations at the grid level. So on the left, we have the ground truth. This is what you see from the simulation. In the middle, you have what the neural net is capable of describing. And then to the right, you have the state-of-the-art application, which is a gradient model. And what we have found is that neural nets outperform gradient models at all levels, either when you have low or high resolution simulations, and we use a different filter to go and study the grid. Whether you use a small or a big filter, neural nets always outperform gradient models. And this is great because this now means that we can go and stick these neural nets into actual simulation codes and try to accelerate this part of the simulation. This is very, very promising. Now, the final challenge has to do with combining HPC and AI in a way to maximize the output of the two. And as a driver for this, let me go back to the case of black hole mergers. So here again, we are going to look at the collision of two black holes. It's, you may think, a simple simulation. You have vacuum, space-time, and you have two black holes and they are moving around each other. It is true black holes require only 3 parameters to be described, but when you look at the parameter space that they span, as I said before, it is a 9-dimensional parameter space. And you would require millions upon millions of waveforms to properly describe these systems. So let's see what happens when we try to solve this problem using neural nets. And let me start with a problem that is feasible to tackle, which is the 4-dimensional problem. 2 masses, and then for the spin vectors of each black hole that has 3 numbers, I'm going to pick only the one that is in the z direction. So when we train a neural network with over 2 million waveforms, this is about 5 terabytes of data, and we use the clusters that are provided by the National Science Foundation in the US, we started with a basic scaling approach. How long would it take to train these models using 1 GPU, which is what most of the community members that are trying to explore these applications are using. So using one volta would take about 1 month to train one of these models. If we use, for example, the HAL cluster on the right of this slide, it takes about 17 hours to train it using 44 GPUs and about 72 hours using 72 voltas, the Pittsburgh Supercomputing Center. So right there we see the need to try to do this at scale, and we have now obtained an allocation in Summit to further scale this and increase the dimensionality of the problem that we are tackling. And so let me tell you about not only doing scaling, but actually doing physics-inspired AI. And here I'm showing you two waveforms. The one to the left is the prediction of one of these networks when we use naive training, which is not that we're doing things as newbies, but that we're not incorporating domain knowledge from general relativity in the loss function. And as you can see here, the neural net can predict the mass ratio of the waveform and the two individual spins. And you can see that for the ground truth, which is just given by the second column for the second row, and then you have the prediction by the net that is q underscore p in the third row of the panel. You see that the numbers are quite different when you when you have binary black holes with very similar mass ratio. And when you're not using physics-inspired optimization scheme, you see that the waveform match or the inner product between the two is very low. If you have this type of overlaps in actual detection scenarios, you simply discard the signal. So this is the difference between a detection and a non-detection. On the other hand, if you now use a physics-inspired loss function, you see that for the same signal, the overlap is above 98%. Or in different words, doing AI plus incorporating domain knowledge gives you an edge when you are using AI to process this type of signals. Now, another thing that we found is that when you study black hole mergers that have asymmetric mass ratios, we know that it is very hard to predict the spin of the secondary or the lighter black hole, just because the black hole does not have a big influence in the dynamics of the binary, and so its impact is very hard to extract. However, what we have found is that when we use neural networks for this type of work, and this is a new finding, when we use neural networks, we can predict the individual spin of the primary and of the secondary with outstanding accuracy. So this is a new finding that, as I said before, could only be achieved because we are combining AI and HPC to tackle problems that individually they cannot address. So just to summarize, what I have presented is the following. We are seeing the emergence of attempts to achieve convergence between AI and HPC. This is a must for domain applications that involve a lot of data, and data that must be processed in low latency. We are also seeing that domain experts are working closer together with AI experts to try to incorporate domain expertise in these models. And this is essential to try to understand how we can maximize the use of AI, instilling rigor, trying to use, for example, Bayesian neural nets or graph models. On the other hand, we also see that AI can be used to accelerate the solution of partial differential equations. And this is very relevant for applications like computational fluid dynamics or multi-messenger astrophysics. And one final thought I want to mention here is that with conferences like this, there is a great opportunity to try to cross-pollinate expertise and experiences that we have. Because while we can share, for example, a repository with data, with neural networks, and even enable interoperability of HPC platforms between the US, Europe, and Asia. The most precious commodity that we can share is knowledge. And sharing this information freely with colleagues is the key factor, I think, that will further boost the application and the use of AI in different domains. And I want just to mention two different collaborations that are doing this with NCSA. One is the Joint Artificial Intelligence and Machine Learning Lab that brings universities across Europe and the US, and also the Joint Laboratory for Extreme Scale Computing that also reaches out to universities in Asia. And we have been able to get in touch with different communities going out of the physics domain that we live in and partner with people in astronomy and computer science. And here is a snapshot of a recent deep learning tutorial that we offer at the AAS meeting. We didn't know how the astronomy community would respond to this invitation, but as you can see, we had to get an overflow room because it was packed. So there is definitely hunger for this type of knowledge in different communities. And as I said before, one of the main goals that we have at the University of Illinois is to create an international network with AI practitioners. And we are doing this with some of these partners. And let me just finish acknowledging the support I get from the National Science Foundation, the Department of Energy, and also from NVIDIA. Thank you.
Thank you, Eliu. It was a wonderful talk. It's so enlightening to see merger of AI and HPC. And now I encourage our listeners to ask questions. We have 5 minutes for questions.
Initiatives are on your international AI network roadmap? And the answer is one of the first few things that we are trying to do is to start training students. We see a depletion of this type of talents because they move quickly to industry. Obviously, they earn a lot more money in industry than in academia. And also the formation of leaders that can lead international and interdisciplinary teams. Those are one of the two main goals. And is there a way to join? Yes. So you can see that I mentioned JLESC. JLESC has a website. Just Google that up, JLESC, and there is a way to join that collaboration. So that would be the most immediate, easiest step that you can take if you want to join this collaboration.
Do we have another questions?
So the question is, how can we use deep neural nets for discovery of new physics in the near future? So this is one great question. There are, of course, a lot of physics phenomena that has not been explored properly. And I just mentioned one, this due to turbulence. Turbulence continues to be a big issue in physics. And we are just scratching the tip of the iceberg. Here in the US, the National Science Foundation had a competition for AI institutes recently, and one of the topics was string theory. So doing data-driven discovery there would be really interesting, not using data, but simulations and different models that are available in the literature. So that's one of the things that people are exploring. Also genomics. There is a lot of data, but the key challenge, as we see in physics, astronomy, and in biology, is the lack of labeled data sets. So one of the key challenges that will permeate all these applications is how we try to get humans in the loop to create these data sets to go and maximize the use of AI. So you will see this as a common thread in the next few years.
We still have time for one more question.
Okay. The question is, from gravitational wave observations, it was possible to determine the effective spin, that is the mass-weighted projection of binary components spin vector. Is the usage of neural network now making possible to break this degeneracy? And let me just clarify this. What we are doing in this initial project is to characterize the signal manifolds. So we are not using noise in the signals yet. This is just at the basic level of saying, if you have a neural net, can you go and measure the individual spins of the black holes? And in the absence of noise, this is a very loud yes. This was not possible before with any other signal processing algorithm for signals that have no noise. So with this analysis, we now have the baseline. Now, the next project that we are working on right now, and I'm not going to present results at this talk, but in a possibly in a talk in the next few months, is that when we incorporate noise, then there is now a bias in how you estimate the parameters. But for now, what I can tell you is one thing that was not possible before was to measure the individual spins when you had asymmetric mass ratios. Now we can do it.